So here we have a beam problem for static equilibrium where a beam is attached to a wall and it's supported by a cable at one end and there's a crate hanging at the other end. And we're going to use the data from the drawing to figure out what the tension in the upper cable is. So in any of these static problems, we need to identify where the forces are, where they act, and in what direction they go. So we know that this cable is going to apply a tension that I'll call F sub t in that direction. This cable is going to apply a tension too, but since this box is held still, its gravitational force, its weight is pulling down on it, so this wire has to pull up with an equivalent force so that this remains in static equilibrium. So this tension essentially is going to be equal to the weight of the crate. So I'm going to just call that W sub C for weight of the crate. And that's going to be equal to the force of gravity in the crate. Curiously, it does not tell us how long the beam is, so I'm just going to call it L for now. There's going to be a force here at this hinge. It's going to be up-ish, because if we had this as our axis, the beam would swing down. So it's got to have some kind of up force. And it's got to be right-ish because this wire goes left-ish, but I really don't know anything about those. There's another force. It's the beam itself has mass. Now that torque due to the weight of the beam is going to act at the beam's center of gravity, and since this is a uniform beam, its center of gravity is in its center. So that's the weight of the beam right there. I'm going to redraw a simplified diagram off here to the side so I can get a better idea of angles and things, because unknown force there, I don't think I can use Newton's second law for equilibrium here. I think I need to use some of the torques. So Newton's second law for rotation, equilibrium, rotational equilibrium to solve this. Right, there are three conditions for equilibrium: that the sum of the forces in one dimension have to equal 0, sum of the forces in the perpendicular dimension has to equal 0, and the sum of the torques about any axis, if this is static equilibrium, has to equal 0. This is what I'm going to use here, because looking this over, I don't know, I've only know 2 of these forces, so I don't think I know nearly enough. Where I think I can figure things out pretty easily with this tension, this torque rather, to find this tension, if I put my axis here. So I'm going to put the axis for this at the hinge or the pivot. So right here, I'm going to make that my axis. That is beneficial because it eliminates any torque due to the forces there at the pivot, which are things I don't know. So I'm eliminating unknowns and things I don't want to know right now either. Well, let's again make a better diagram. So I'll do that over here. We've got our beam. We've got this weight of the crate. We've got this, the weight of the beam. We've got this, our tension. Now, torques depend on distance from the axis, force, and the angle that radius, that lever arm, makes with that force. So I need this angle for those. I'm going to call that theta, and I need this angle for that one. I'm going to call that psi. Now, thetas, if I look here in mine, they give me this angle is 30, so I know that these are 60 because they're complementary angles. So theta equals 60 degrees. Then psi up here, well, this is opposite exterior angle, so that's a 30. So 50 and 30, that's an 80. This is equal to 80 degrees right there. And this just allows me to use the the definition of torque, since the torque due to the force is RF sine of the angle between R and F. Now I've got to add these all up though. So I'm going to take counterclockwise as positive, so we've got the torque due to the crate plus the torque due to the beam minus the torque due to the tension. That all has to add up to 0. Now since I took my axis as the pivot, that's the distance I have to measure my radius from, or my lever arm from, for the crate. So I'm going to have R for the crate is going to be, let me write that out, R for the crate plus the force of the crate times the sine of the angle that it makes plus R for the beam, the weight of the beam, the sine of theta, and I'll move this over here, is going to equal the R for my tension force, and the sine of psi, because that angle is different. This angle in here always has to be the angle, if you're using sine, if you're using RF sine theta, it's got to be the angle between the distance from the axis, the lever arm, and the direction of the force. You don't have to use sine if you have other angles. You need to find the perpendicular component is what you need to find. And we can do that in multiple ways, but we're going to stick with this for now. All right, let's put in all our numbers. We don't know how long the beam is. We're just going to call that L. So the crate is all the way out at L. The crate has a weight of 2,000 newtons. And then we want that angle there, which is 60, sine of 60 degrees, plus the beam's distance. Well, it's at half. It's at L over 2. And it is 1,000 newtons. And the angle that that weight makes with that lever arm is 60. And that's going to equal the R for my tension. That's all the way out at L also, all the way at the end. And that tension is what I want to find. And the tension makes an angle of 80 degrees with the beam. Well, all right, we didn't know the length of the beam, but it turns out here that everybody's brought an L, so these L's actually reduce down to 1. It doesn't matter what the length of the beam is to solve this problem. So we see that I'm just going to divide the 80 out over here. We're going to have the 2,000 times sine 60 plus the 1,000 over 2, 500 times sine 60 divided by sine 80 is going to equal my tension. So let's plug in all those numbers and check out the answer. I get 2,198 newtons. Now this is all one significant digit. These are 3 technically, so I'm just going to make it 2 for now. The tension is right there, which you can barely see at the bottom of the screen. If I screen down, right there. All right, 2,198 newtons, or 2,200 newtons is that tension. So there you go. I hope that's helpful.